Hey there, welcome to a video discussing section 5.3, which is going to be on first derivative test for local extrema, concavity, points of inflection, second derivative test, and interpreting graphs. We're actually going to do, just want to make sure I'm sharing my screen, sorry about that. We're actually going to do the first two pages here. So we're not going to quite get to concavity. We'll start with that on class the next time we meet. But remember back in section 5.1, which actually was not that long ago, we said that extreme values only occur actually at endpoints or critical points. Remember, critical points are when f prime equals 0 or f prime does not exist. And that's where we went looking for local and absolute extrema. We also noted that just because we had a critical point, we may or may not have a local max or min there. That was the case with this one right here, or in this one right here, we have a vertical tangent. We have a vertical tangent or a stationary point. We didn't have a high or low. I mean, yes, the derivative is 0 here. The derivative does not exist here. But just because you have a critical point where derivative 0 does not exist doesn't necessarily mean it's a local max or min. But here we do have a local max, and here as well. So we need to find a test that will help us determine when f prime or when f prime does not when f prime equals 0, f prime does not exist, will be a local max or min. So let's look at the following graph for inspiration. It's a pretty wacky graph down below. And we'll have to be true about f prime at a critical point for there to be a local max or min. Well, focus on what's going on with the derivative. This is a derivative, by the way. It's kind of hard to read. There's a prime symbol. Before and after your critical point. So this is your first critical point, C1. Now in this case, f prime was positive before we got to C1, and it's positive after we pass C1. F prime did not change sign, so then therefore f does not have a local min or max at C. But let's look at C2 now. The derivative was positive beforehand, then negative afterwards. So it's kind of like a roller coaster going up and then down. So then we say f has a local max at C. Then let's look at C. So this is at C2, and here is at C1. So again, at C2, we went up, then down. So the derivative was positive before we got to the high point, and then negative. So, I mean, by looks, we could tell it's a local max, but analytically, f prime changed from positive to negative. You have a local max. Now at C3, what if my derivative was negative before I got to that critical point, and then positive afterwards? That's what we call local min. And remember, critical points are x values where the derivative is going to be 0, does not exist. So the derivative is definitely 0 at these locations, at C1, C2, C3. But you had to really investigate what was going on with the sign of f prime, whether it's positive or negative, both before and after you reach that critical point. Of course, if you keep looking afterwards, C5, the derivative is negative before and after, so that's why there's no extreme value. At C4, obviously, the derivative is positive and negative. Now, that is going to be undefined. That is a corner there. And in fact, it's going to be our absolute max because it is the highest y value in our interval from A to B. And of course, at the left endpoint, it's absolute min. Our right endpoint, we actually call a local min. We're going to talk about endpoints very shortly. Oh, another thing you have to assume as well, you have to assume f is continuous at these points you're looking at. Not for the whole interval, but I mean, that's for extreme value theorem. But to find local mins and maxes, obviously you need to be, not obviously, but you do need to be continuous at the point where you're looking for a critical point, when you're investigating a critical point. Now let's talk about endpoint, and then we'll do an example so you guys actually see this in action. And here's the don't bother to memorize, just use common sense. So these are for endpoints. So let me replicate the graph we had on the previous page. It was kind of like this, and it did some sort of wacky things, you know, like kind of like that, and then there was like this corner, kind of looks like Half Dome. I do miss Yosemite. That's a fun place to go to. Hopefully, get back there once the virus is gone. Sorry, I digress a little bit. Yeah. So anyway, our left endpoint. Let's take a look what's going on there. If your derivative is positive, so clearly f prime is positive. When we're a little bit to the right of A. So if f prime is positive, then f has a, what we say, a local, hold on a sec, a local min. So I was looking at the wrong place. So we call this a local min at that endpoint right here. Now, what if I have this reversed? So I have something kind of like that. And that's A. So right after I pass x equals A, my derivative here is negative. So in this case, we call that a local max, because this is obviously higher than the stuff immediately to the right of it. So if f prime is negative after you pass the left endpoint, then we call it local max. Whereas f prime is positive after you leave the left endpoint, then it's a local min. At a right endpoint, so you can see that we're diving down. Our derivative is negative right here. You have negative tangent. So in this case, when f prime is negative before you get to the right endpoint, we're going to call that a local min. Where our derivative is positive right before you get to that endpoint at point B. So f prime here, of course, now is positive. We're going to call that a local max. So again, don't bother memorize, just kind of use common sense, just kind of see, okay, the derivative is positive afterwards. Yeah, so it's obviously that's the local min because that's a low point. And if it's negative before you get to a right endpoint, they have that. Now, if the derivative is negative after you leave the left endpoint, then that's a local max. If derivative is positive before you get to a right endpoint, then that's also local max. So use the first order test to find any local extrema for the function. Will these be absolute extrema? Support your answer graphically. Okay. And actually, let's do an accurate graph of this too. I think we're ready. I think we're ready to actually, do this without a calculator. And that's what we're going to spend a lot of time on Thursday doing, or the next time we meet. So use the first order test to find any local extrema for the function that you see right here. So first off, you're going to do your derivative. And let me give you the steps, actually. So let me clear this. Let me do a little text box. Let me write out the steps. So I'm just having up steps. Give me a sec here. Okay, sorry for a little delay there. So here are my steps. So we're going to find our derivative. After we find derivative, set equal to 0. And then we're going to solve for x, which are the critical points, and also see if f prime is undefined anywhere. So f prime is going to be easy, 6x squared minus 6x minus 12. Set it equal to 0, that's the second step. And at the same time, I'm going to factor out 6, might as well. Then I'm going to solve for x. That's easy, just easy factoring. So x equals 2 and negative 1. Those are my critical points. So I've done steps 1, 2, and 3. Done, done, done. Make a sign chart. So here's negative 1, here's 2. And what you're going to do is you're going to start with the rightmost interval. Let's say I plug 3 in for x. If I plug in 3 into x with my derivative, I get 6 times 1 times 4, that's positive. Now, you could keep testing points into other intervals, but there's a little trick you can do to be efficient here, and that requires just a little bit of critical thinking. What you could do is you could say, well, at x equals 2, that came from x minus 2, that's linear. There's no like squared symbol or like an absolute value that keeps it positive. So I anticipate the sign will change for the derivative to left of 2. And x plus 1 comes from, negative 1 comes from x plus 1. That's also a linear factor. So that's also going to see a sign change because you're not like squaring the x plus 1 or you're not putting an absolute value around it. We'll have that discussion in more detail on Thursday. But these will alternate because of the nature of our derivative, the way the factors worked out. So we see that the derivative, now we make our statement for 5 and 6. So the answer is yes, there are, we don't know about the absolute part yet. Sorry about that. Let's focus on just find the locals. So because we go from positive to negative, you have a local max at negative 1. So the way you're going to write it, and you want to write it in a formal manner, you're going to say there's a local max at x equals negative 1 because f prime changes from positive to negative at x equals negative 1. And this is the AP saw. This is very formal. You have to write it this way. So now we do it right below in blue for local min. That's a 2. You have a local min at x equals 2 because your derivative is going down, right? It's negative beforehand. It's kind of like a roller coaster. It's going down, then up. So try to visualize that if it helps. Local min at x equals 2 because f prime changes from negative to positive at x equals 2. So you got to say it like that. They're very particular about that on the AP exam when I say they, the College Board. Now, will there be absolute extrema? Well, the thing is that our interval is open. We don't have a closed interval. And think about the end behavior. Maybe you might remember this from Algebra 2 or pre-calculus. Because you have an odd degree and a positive leading coefficient, the graph's going to kind of look something like this. And I'm not sure if we can actually find the x-intercepts easily. I don't think we can. So it might be a little hard to do a super accurate graph, but I know I have a y-intercept of 0. I do know that our graph is rising until we get to negative 1. And if you were to plug negative 1 into the original function, I think that's going to be, see, negative 2 minus 3 plus 12, so that's 7, I believe. So graph kind of does something like this. And then it's going to start dropping until I get to x equals 2. And if I plug 2 into this, I think I get 16 minus 12 minus 24. So it's actually going to be pretty low. I didn't go low enough, but it's going to be negative 20. That's how low it dips. So let me redraw that. So it dips down here and then just goes up after that. Then it just rises forever after 2. So given the end behavior, the left end going down forever, right end going up forever, and that's just using the limit as x approaches negative infinity and positive infinity. You can just think about numerically what's going on with y when x gets really negative, when and x gets really positive. Yeah, I mean that's just what you get. And so these are not. So there are no absolute extrema, and obviously my graph kind of supports that. Again, we don't have a closed interval, so we're not guaranteed to have absolute extrema, but we do have locals. We had a local max right here and a local min right there. We're going to do a lot of this stuff. And actually, we didn't quite do a super accurate graph. I kind of lied. When we talk about other things in this section, like concavity, points of inflection, second derivative test, that's when we'll actually be able to take something like this here and generate graphically without the aid of a calculator or Desmos. Okay, so that concludes the video.